So the problem with allowing this spark to happen across here is if this is not a mechanical switch, we can build switches out of electronic devices as well. This is what we use transistors for. And a transistor is a rather small, delicate device. And so if I go in here and I somehow cause a huge spike in voltage to occur, very, very likely I'm going to destroy that transistor that's used in this position right here as an electronic switch. So the way to deal with this is to provide a place for this current to go. Here's this current that's flowing through this inductor. And the magnetic energy that's stored around this inductor is going to force that current to flow, even if we open this switch. And in the case here we saw when we open a mechanical switch, it sparks right across there. So the inductor wins. The inductor current wins in that case. And it can be very damaging to whatever's in this position down here. The best way to solve this is with a device called a diode. And this is another semiconductor device. It's not a switch, but a diode has an IV curve. Here's V, here's I, and it looks like this. The current, I'm just going to sketch this. The current is 0 when the voltage on the diode is negative. And somewhere around here, the current goes up like that. So when we have a diode, this is the symbol for a diode, like that, and that's plus and minus V, and this is the current through the diode. So positive current and positive voltage is in this part of the graph over here, and when I have a positive voltage, this is about 0.6 volts, something like that. Could be 0.5, can be 0.7. When you have a positive voltage on this, then the current starts to flow freely through this. If this voltage goes negative, so that means that this voltage is higher than this voltage, then the current actually goes pretty much to 0, very, very small value. So I'm going to take advantage of this diode device to help me with this problem I have over here with the current. And the way we do that is we do this. We hook up a diode pointing in this direction here. Pretty distinctive. But anytime you have a circuit that has an inductor in it, so it's a solenoid or a motor or a relay, this is a way you can protect the devices driving your coil. So let's look at what happens here when we push this push button down and let it go again. When we started out, we had no current flowing. The push button was open. So there's no current going through here. And there's no voltage difference across here. Both of these points are at 3 volts. And so there's no voltage across the diode. And that's that point right there. No current, no voltage. So all the currents are 0, and the voltage across the diode is 0. So there's no current. Nothing's happening. Now we push the button down, and a current starts to flow through the inductor. And there's 3 volts across the inductor. So let's look at that. There's plus 3 volts here, and there's 0 volts down here. So there's 3 volts on this side of the diode. This is the side where it doesn't conduct. That 3 volts represents negative 3 volts across the diode. Let me mark the diode voltage on here. Here's minus, plus, V diode. And we'll call this V diode. So this is a V diode of negative 3. So we're operating over here out at negative 3 volts on the diode. And the current through the diode is 0. There's no current flowing over here. All of this current is going down and going through the inductor and doing whatever this inductor is supposed to do. Okay, now we open the switch. Now we open the switch. And as you recall a minute ago, what happened was this voltage right here, this voltage went big. This went plus big, and we had like 100,000 volts or something. That's where it was headed. Well, we're not going to let it get there, so I'm going to take that away. So this voltage here, as soon as this switch opens, this voltage right here, this is headed up. This is going up hard. But we're not going to let it get very high, and that's the job of this diode. So as soon as this voltage here gets to about 0.6 of a volt higher than right here, so when this voltage gets to 3.6 volts, what that means is that the V diode now equals about 0.6 volts, right? This is at 3 volts. This is at 3.6 volts. So V diode is 0.6 volts. And that puts us about here on the curve. And what's going to happen is this current that we had here, this current that was flowing down through this inductor is going to do what? It's going to go this way. It's going to flow this way through the diode. And that's this portion of the curve right here. And it'll keep going like that. Look at that. We provided a current path for this inductor that's not going to destroy what's down here. The highest voltage this will get to is whatever voltage it climbs to on this diode curve here, which is going to be between 0.6 and 0.8 volts. So the highest this is going to get is 3.6 to 3.8 volts. And typically a transistor down here will easily withstand this kind of a voltage on its terminals. So this is called, the effect of having this voltage go way north is called kickback. That's kickback from an inductor. This diode is a protection diode, and basically what it does is it supplies a pathway for that inductor current when this voltage goes above the top end of the inductor. So whenever you build something that has an inductor in it, it could be you could build a circuit that drives a motor or an actuator or a solenoid or something like that, or part of a robot. This is one of the circuits you want to keep in mind. Whenever you have an inductor and you're going to switch it on and off, you want to design in a diode like this to protect your circuit from those unstoppable inductor currents.